you're live.
Thank you. All right, hello everybody, welcome. I think y'all pretty much know I am Professor Almand. And I want to talk to y'all about a very interesting way of looking at quantum mechanics. I am going to give you a little warning ahead of time. Some of this stuff is a bit hand-wavy. I'm not doing any math. And when I say quantum mechanics, if you go looking any of this up, I'm using that term to cover everything quantum. That includes, quantum mechanics. That includes quantum electrodynamics, quantum field theory. Basically, all of those things. I'm just kind of lumping into one here because I don't want to get down into like the nitty-gritty of splitting them apart by whether or not they're relativistic and such. And hopefully, then it just kind of gives you a sense of the strangeness, I guess, of quantum mechanics. Okay, we ready? So we're going to start off fairly basic. Take a look at this. We're going to start talking about transverse waves. So, in fact, originally quantum mechanics was going to be called wave mechanics. So this is why we need to get into some wave stuff to start with. I think you've all seen this kind of a wave. It's kind of like if you just took a string and you started shaking it up and down, and then you could see the wave travel along, and I tried to make like each picture look like it was, the wave was, moving along further that way. Okay, so waves on a string, it's gonna be that one. What I went ahead and did is I put a red mark on the string, and what this is trying to show is that if you look at that red mark, it's like I took a piece of red tape or something and put it on the string. As you send the waves through the string, that red tape or that red mark is only going to move straight up and down. It's not going to actually progress down the wave. Waves carry energy; they don't actually cause an overall displacement. And so you can see that there with that dotted line there, that those all stay nice in a straight line. And then I thought, well, what's better than this? Actually, I guess I thought, put arrows in there for it going up and down first. So then I thought, hey, what's better than that? And I hope I did think it after this right here. Yes, I did. I thought, hey, let's show you this actually working. So what I have here is just a recording of a simulation I made with some waves that are connected essentially like by springs. And as it goes up and down in waves, you can watch the little white dots, and you can see that they move straight up and down. They don't move side to side. So, okay, and you can see especially that one on the end is just going straight up and down. They all go straight up and down, even though the wave you can see moves along towards the right. No applause, please. Okay, you want to see it one more time?
Yeah.
Okay, I thought so. I actually have a simulation to this if you're in my physics class or anything that you can go to and get on this and put different waves on it and stuff and see what they do. Make them reflect back and all kinds of stuff. So feel free to look at that. Oh, I just played it again. There we go. So then we also have longitudinal waves. These waves are different. With the transverse waves, as the wave went up and down this way, the actual wave propagated along that way. So the medium was going like this, the string was going like that, and the wave was traveling down this way. For a longitudinal wave, the wave propagation, the way it moves, is actually parallel to the direction that the medium is vibrating, that it's going back and forth. This is very easy to see with a slinky. If you've ever had a slinky, you stretch it out, and you take one in, and you just start doing that with it. Start shaking it. And what happens is you start putting compressions on it. So that's what this little first one was. There's the first compression. And then as you pull it back, it stretches out. And then you push it, it compresses, and pull it back. And you keep doing that, and what you get are these alternating regions of these compressions and these stretched out regions. And the stretched out regions pull the compression part down. And so the coils themselves end up right where they were before you started. But you can see, it's pretty interesting. I just didn't think I could do it here today. It's pretty interesting. You can see like the little compression travel down through the slinky. And that's longitudinal waves. And the reason we're doing all this is to bring us to something more like ocean waves. All right? Ocean waves are essentially a mixture of the two. When a wave goes through the water goes up and down, and it also moves forward and backward like the longitudinal. So if there was like a piece of seaweed or something floating on the ocean and you watched it, it would actually go in a circle, like a circular motion as the wave passed it. Ultimately, it goes back to where it was, but that's what it does. So this was our first picture here, and as this wave was passing, I tried to make the arrow point to like the same like little bit of where a piece of seaweed would be, or the same little bit of water, and you can see it makes it go around in a circle. And this kind of circle idea for representing waves is going to be very important for us in just a little bit when we start talking about the main thing we're talking about. Okay, we're doing okay so far? Nothing too bad, right? All right, the next thing we need to talk about are wave reflections. Okay, so when a wave encounters a boundary, you probably know this, like if you've ever yelled somewhere and heard your own voice come back at you. What's that called? Echo. Very good. Yeah. Okay, y'all are on it. An echo, that's when the sound waves, actually, which is what the longitudinal waves are, they hit a medium and then they reflect. And so anytime a wave encounters a new medium, which is what it's traveling through, you get some of it that transmits and some of it that reflects back. And if that boundary that it's reflecting off of is what is called a fixed boundary, then what it does is it causes the wave that bounces back to flip over. So all the high points, which we call crests, they become the low points, which we call troughs. Okay? And they do that, it'll flip over. Y'all are fine, come on in. Your coffee. And then we can talk about wave interference. This is when waves meet up with each other. So you can see here at the top, I have two waves, different heights, going toward each other on a string. This is like a transverse wave. This also works with longitudinal waves. It even works with light waves. And as they approach each other, they eventually overlap. And when they overlap, I left dotted lines in there to represent the two waves. When they overlap, they combine into one big wave. They'll add up. Okay? And when they do that, they add up, they make a bigger wave, and then afterwards they go on through each other and they turn right back into the waves they were before and keep going as though nothing ever happened. What's really interesting about this is if you send one wave that's like a crest, a high part, and one that's a trough, is they'll go in the middle, meet, and totally cancel out, and it looks like the wave disappears before they suddenly reappear and just keep going on their way. All right, so waves are kind of interesting like that. So that's what that one will do. And here is that actual thing. I probably should have changed the page before I talked about it. But yeah, if you have two waves that are the same height, one is a crest, one is a trough, they basically cancel out. It's almost like adding positive and negative numbers. You think of the troughs as negative numbers, the crests as positive numbers. If the crest is one high and the trough is one low, that's 1 plus negative 1, it gives you a 0 when they overlap. If it's 2 high and 1 high, it gives you a 3. If it's 2 high and 1 low, it gives you a 1 high. Like it just adds up. Again, like positive and negative numbers. And then they come back and they go about their merry way. This brings us to standing waves. So, what we can have here is on the right there, you're right. I had it correct. Up there at the top is basically a string, and it's clamped at both ends. And what we're going to do is we're going to add vibrations to it. If you want an example of this, think of a guitar, think of a violin, any stringed instrument is going to do this. And so we're going to add some waves on there. So maybe we take one end, like a guitar normally, you just pluck it in the middle and you let the waves that are going to happen occur on it. But we're going to put very specific waves. So we're going to attach something to one end, and we're just going to have it just move just a little bit, real fast. And at first, we just let it go normally. And what you get is you get a jumbled mess. Okay, and that's that picture right above it, or right below that straight line there, okay? It just, the waves go, they bounce back and forth, they're always kind of meeting strange, and you just get a jumbled mess, and it's nothing too great. But if you slowly start picking up the speed and going faster and faster, what will eventually happen is you'll end up getting something that looks like that third picture there. almost looks like a jump rope, right? Right, you're basically making a standing wave with a jump rope. What happens, anybody ever do jump rope? And you have to go at a certain speed, right? If you just try to do like that, then it just gets to be a jumbled mess. It doesn't work, right? Well, it's the same sort of thing here. You have to get that proper speed on there. And then what happens is you're sending one wave in, and then it reflects back and it inverts, and it inverts and comes back right as the other part of a wave, as you send a crest in, a trough in there, and then they add up and they make it bigger. And then they reflect back as crests, and they add up even bigger. And so you get this kind of back and forth as they keep adding on to each other, and you get this very big wave even though you have a very little input. These are called harmonics. All right, these are what happens like if you pluck a guitar string. You pluck a guitar string, it kind of looks like that, doesn't it? And it's just going up and down in the middle like that, real fast, and it kind of blurs out and everything. If we then go past that point and we speed it up a little bit more, we get back to a jumbled mess. All the waves start just making jumbled patterns, and it's nothing very well. But if we keep going, we eventually get that next picture where it looks like two guitar strings or two jump ropes. Okay, that's the next harmonic where we get a full wave on there, and it starts to make this harmonic wave under this we call them standing waves like that. If we continue on, getting it faster, we get back to a jumbled mess, and then we eventually have this happen. Right? And then we get the three of them on there like that. And then if you make it even faster, it gets to be a jumbled mess. You go even more, you eventually hit 4 of them. You go a little bit beyond that, it gets to be a jumbled mess, and then suddenly 5 appear. And then there's a jumbled mess, and then 6 appear. And you can keep going like that. Now, why in the world am I telling you about this? Well, probably, you probably know this, especially because you usually learn this in chemistry. But this is essentially the reason why we have these specific orbitals, okay? And that's the kind of thing we're going to talk about today. It's going to be this quantum mechanical wave thing that makes these orbitals. So you can see you have these s orbitals at the beginning. They're like that first picture up there. It's like that first harmonic. This one is like that middle one over here, that one. They get to be more complicated after that. But essentially you have the electron that has some sort of weird wave nature to it, which is what we're here to try and understand a bit today. And it basically goes around the nucleus like it's on a string, like it's trapped on a string like the wave is, and it interferes and it makes specific places where it's very stable and works, and if you try to go somewhere in between, you get the jumbled mess and it's not stable. So the electron tends to stay in these stable orbitals and nothing in between them, right? That's why we have those specific shells that you have, right? What other orbitals do we have?
SPDF. GHI.
K, L, M, N, O, P. Also. All right. So, it turns out that these wave properties seem to be found in all types of particles. So at first it was found in light. You maybe have ever heard of it. It's the double slit experiment, and you send light through it, and you get this interference pattern like we were seeing with where some of the light adds up and makes it really bright, and some of it totally cancels out and makes it dark, and then it bright and then dark and bright and dark. But it turns out then we kind of see this with everything, with electrons, with all kinds of particles. They all seem to have this. And again, I think I mentioned this earlier, that this was almost called wave mechanics because of this, but it eventually got quantum because this caused, like we saw on the previous page, causes all these orbitals to get quantized, specific ones that can exist. All that just so you now know the name, right? These are not physical waves. All right, they're not like an ocean wave. This is not like you could look down and see an electron and it's going along in a wave. That's not the idea here, okay? They are not probability waves. I hear people say that one a lot, that it's a probability wave. It tells you what the probability is of finding. Have y'all ever heard that? Yeah, that's not it either. These are actually complex waves, all right? They are things that we actually cannot measure. Right? No one's ever gone down and measured these waves and seen these waves. They are pretty much mathematical entirely, okay? And they are complex. They have imaginary numbers. We can superimpose them. We can make them add up and cancel out, just like we were doing with the other waves. And if you then take that, after you add them up and do it, you can do some more math to it and find the probabilities of where it's going to be. You can get a probability distribution out of it, but the actual waves in quantum mechanics are not the probability waves. Okay? They're just a mathematical structure. And if we get to the end and I haven't talked too much, even though I can't see that time because something popped up in front of it.
Oh, it's 4:31.
What is that?
Low power mode.
Oh. So, let's take a look at why we're all here. And that's mirrors. We all like mirrors. We all want to look at ourselves. We all want to look at things in mirrors. So let's talk about mirrors. And first thing we're going to do is we're going to look at the classical explanation of how a mirror works. So this line down at the bottom, that's my mirror. Real fancy, right? No, I did not take any graphic art courses. Learned that all on my own. It's impressive, the realism though, isn't it? And what we're going to do is we're going to divide it up into little sections just so we can look at what's happening at each little spot. Okay? So those little dots there, they're not actually part of the mirror. I just put them there for visualization. Just, chemists are in the room, so gotta make sure. All right, we're gonna have something over here that is our light source. For right now, we're just gonna use something like, I don't know, it could be a laser, it could be just a light bulb, it could be, it could be a person's face, whatever it is. We're gonna have something there as our light source, and then over here, we're gonna have a light detector, which typically the one you're most familiar with is your eye. Your eye detects the light that bounces off of a mirror, okay? But we're gonna use a detector thing here that when a little electron or when a little photon goes into it, it hits and it makes a splash. And it splashes these electrons off and it makes more of them, and then they go up and they splash even more, and then it splashes more, and you end up like with this big electrical signal just from a tiny little bit of light. Little photo multipliers, okay? And this is essentially the classical explanation of what happens. That right there, that very realistic looking beam of black light, is how we would say the light that the detector would pick up. That's the path it would follow. It would go down right in between the two and bounce up. And in fact, it bounces up at the same angle that it enters in at. So if we draw in a vertical line there, from normal to the surface, this little angle between this incoming wave right there, this incoming bit of light, is going to be the same as this little angle over here. It comes in, it bounces off at the same angle, and that's how we can tell where our little beam of light is, where it's going to go. Now, other beams of light, since this is a light source, it's not necessarily going to just send out the one that perfectly goes there. All the other light beams that would come out of it, all the other little beams of light, none of them are going to hit the detector. So the detector won't see them. You wouldn't see those light beams. You would only see the one that came out of that angle and went up into your eye. All the rest go off somewhere into the universe. We don't know. Whatever happens, depends where this is and what's going on and all that kind of stuff. But they spread out and they go on their merry way. Okay? So this means that if we want to see our light source, we really don't need much of a mirror. We can take and get rid of all the sides of it, all the parts that were over here to the left and to the right that just set light off that didn't go to our detector, and we can get just as good of a reflection by just having that center there. So if we were shining a light or something, or a laser light, we were bouncing it off there and having it bounce over there, it'd be just as bright if all we had was that little center piece of the mirror. Seems perfectly logical, right? Okay. So that is the classical explanation for how mirrors work. We're going to now look at a quantum mechanical explanation for how a mirror works. Now this comes from Richard Feynman, and I'm a pretty big fan of his as far as his scientific philosophy goes. And this explanation he gave for this, I remember I had to do this in undergrad, and then I watched an explanation he gave on this, and it was just fantastic to me. And the way he viewed quantum mechanics was just, I thought it was great. So in quantum mechanics, we don't say anymore, we have the same setup, we just have now the quantum mirror. We don't say that light has to go down and come off at that same angle. Right? Light could take any path. It could come straight down, hit, and go over to the detector. It could go a little bit over there and then into the detector. Or there, right through the middle into the detector. Or over there. It can take any path. In fact, any path we could draw that comes down and hits this mirror anywhere, we could draw a path that goes over to that detector. And the idea is that we have to worry about every single one of those paths, not just the ones that go to the middle, okay, like we would in the classical sense. So from this perspective, we should be seeing every bit of light that comes off it, kind of a thing, right? It seems kind of weird. So what's going on here? Well, let's imagine you had a wheel that was rolling. Okay, now you see why I wanted to show you the circular waves, right? So if you have a wheel that's running, let's say we have an arrow pointed on it, as it rolls along the ground, that arrow is going to point in different directions. And depending on how far it has rolled, will determine what direction that arrow is pointed at that moment. And this is kind of like that circle on that wave, where as that wave travels, that arrow points in a different direction depending on how far that wave has traveled, that ocean wave, right? So we're going to do the same sort of thing here. We could actually go in to each and every single one of these possible paths that it could follow, and we can let our little wave go along there, and we can visualize this by looking at a little spinning vector thing, that little spinning arrow as it goes along, like it's rolling along there. And then what we can do is we can watch it roll all the way along, go back all the way up to there, and then when it reaches our detector, that arrow is going to be pointed in a certain direction. And that direction that it's pointed is going to be based on how long of a path that was, the length of that path. Okay? If we make it longer, then it rolls a little further and the arrow's pointed in a different direction. If that path is shorter, then it doesn't roll quite as much and the arrow's pointed in a slightly different direction. Does that make sense? So if we do all of these paths, of course they're all different lengths, so when the little circle arrows arrive there along each possible path, they're all pointed in different directions. Okay, so they're going to be pointed in different directions by the time they get there. So let's take a look at that. Oh, that QMM is quantum mechanical mirror. Just making sure. Okay, so let's take a look at this. Let's say we went through and we took that red path. Okay, and we came down here, we're going to make a graph. So this is like our mirror again. But right here, what this is going to be is this is going to be the total distance that the light has to travel along that path. The length of that red line, going down and back up. And then we can go and we can measure the length of the green line. And it'll be a little bit shorter. And then the length of the black line and the brown line and the whatever that last color is, a dark green or something. And they're all going to have different path lengths. Well, not totally different, because this starts to look symmetric. It starts to go back up. And so what you get is you get this, we start off with this really long path, and then it goes to short paths, and then it goes back to long paths. And if we extended this mirror out even more, like infinitely, we could have even light rays that came like way over here and bounce over, and they have an even longer path length. So this kind of just goes up like that forever. And if we did it for every single point along the mirror, we would get a shape like that for the different path lengths that it would take. Still with me? Okay. So let's take a little closer look at this thing. Those are all our path lengths. And what we're going to do is we're going to go down along the bottom. Now, I arbitrarily kind of did this. I did not go through and actually work this out mathematically, so don't expect this to all be to scale and everything from here works out exactly like it should. I didn't do the math for this. I told y'all, I said put that in there. No math. So I didn't even do the math. I just kind of drew these in. But let's say the first arrow goes and it ends up getting there, and when it gets there, it's pointed in that direction, along that first path. And then say the next path, it gets there and it's pointed in that direction. And then the next path, it's in that direction, and the next in that one, and that one, and that one, and so on and so forth. And we go through and we map out all the directions that the arrows are pointed by the time they reach the detector along each path. Okay? Good so far? Good still? I guess. All right. Now we need to look at adding these up. So we get a little vector addition. slight bit of geometry, I guess, right here. But essentially, we're going to make this real easy. We have a few vectors over here. These are like our arrows. They can be different lengths. All the ones we're going to do for the mirror, they'll all be the same length. Because it's all the same light, it has the same amplitude and all that stuff. But if we want to add two vectors together, A and B, we basically put them, we lay them, we can kind of move them and put them in a path like A and B is there in this picture, like a walkable path, I always tell my students, where you can start at the very first one and walk along A and then walk along B. And then if we draw a straight line from where you started at the beginning of A to where you ended up at the end of B, that new red vector that's there, we'll call it R, is what we call the resultant vector. It's the sum of vector A plus vector B. So they don't add just like normal numbers. 4 plus 3 is 7. A 4 meter long vector and a 3 meter long vector do not necessarily equal a 7 meter long vector. Okay? Because they have these angles in them and you get stuff like that. You also can change the order of them. We can do B plus A. And notice I made the same red resultant because A plus B is the same thing as B plus A. We just took a different path, but you'd end up in the same place. So it doesn't matter what order you add the vectors in. Then I added a couple more vectors there where we could go in and add in multiple vectors. So you basically just start adding the first one, then the next one, then the next one, and then you draw that line from where you started to where you ended. And that's your resultant. We could do A plus B plus C plus D. You could change their order or whatever you want, and you get a new resultant. So we can just basically start going in and it's almost like just stacking these. Here's the first, here's the first arrow, here's the next arrow, here's the next arrow, here's the next arrow, and we can figure out then what their sum is, and their sum is where you started to the very end of the last one. Is that clear? Okay. So we're going to do that. We're going to take all our little vector arrows down there along there, and we're going to add them up. I did not actually take those specific vectors and add them up. Again, those were just ones I chose arbitrarily. But we're going to do it anyway. So let's pretend there's our first vector. And then there's our second one. And then there's our third. And there's our fourth, fifth, sixth, seventh, eighth, bunch of them. And it starts to make a shape like this. And then as you get towards the center, right? I'm going to go back real quick. As you get towards the center, notice those center vectors, those are kind of lined up. They're all pointed kind of up, right? Because along that bottom path is not that big of a difference in distance that it has to travel. So if we go back to this, we keep adding them up, we get around towards the center of the mirror, and they all start to kind of point in the same direction. Until we start to get past the center, where it starts to get to be a longer path length, and it starts to spiral around again. And again, if our mirror went on forever, these two ends would just spiral and spiral in forever. Okay? The name is escaping me right now. The name of this thing, I knew I should have written it down. But it is a very famous spiral of vectors from that graph. So but I'll try and remember it and let y'all know if it pops into my head at some point. Okay? And what we can do then is you could draw an arrow from the very first vector, right where we started, all the way to the end of the last vector. Oops. And you could see that we have something pointing from like right here. Probably should have put that in there and pointed up to there where we ended. And depending on how big your mirror is, it just keeps spiraling around. But the point is, even though you keep making your mirror bigger, these end ones start spiraling. Okay? And if they're just spiraling, they're basically going in circles. Which means you're not really making any progress, are you? So the edges of the mirror outside of the center, all they would be doing is making a bunch of vectors that keep sending you around in a circle. It's like a bunch of waves that just keep canceling out. Right? They just keep canceling out. So if we go back to this, we can kind of see that really all we need is the center part of this mirror, just like we found in the classical case, right? Remember that? All we needed was that center one because that's where the light went. But here we can go in and just take the middle part, and we can lose all of these ones on the ends that are just spiraling around and canceling themselves out. They flatten out, right? Because essentially we can come back here And if we just cut that end off and cut that end off, we still have that same big long vector. And so it makes no difference. The ends aren't making a difference. Okay? So we chop that out and we've got this. And now we're like, well, great. Now we just have the same exact result that we had with the classical case. But not exactly. Because what we can do is we can go back to our full mirror and we can go along, we look at the middle, and you notice those vectors are all pointing upward. And so what I'm going to do is I'm going to go along and I'm going to start picking the vectors that are kind of pointed in the same direction as those ones in the middle. And I'm going to start eliminating the ones that are pointed more down, that would be canceling out. These are like, it's like I'm going to go through and pick all the trough, or all the crests, and cancel out all the troughs. So I'll say, you know, I'll pick that one. That one's going to go bye-bye. You know, that one, that one, that one, those ones right there. So I'm going to go through and pick those ones that are down. And again, this is not the exact shape you would get for where you should do this. And I'm going to go to those spots on the mirror. I'm going to put holes there. And so I put holes in this mirror like this. And now the vectors that are left are all basically pointed upward. And they are helping to contribute to that wave addition at the end now. I maybe could have gotten rid of these ones at the ends too here. I guess they're kind of sideways. But if you go through and you find the ones that are causing it to cancel out and reducing your overall wave, and you put holes at those specific spots and leave the rest of them, then you should get something that adds up even more. Because now around those spiral ends, they're not spiraling anymore because we've taken the parts that make it go back down and spiral, and we just have a bunch that are all pointed upward. And we get a longer total vector, which means we would get a better image. And this is what quantum mechanics says should happen. This is the big difference between the prediction of what classical would say and what quantum would say. Quantum says, go into certain places in your mirror, put holes, get a better reflection. Classical says, don't put holes in it. Like, that's not going to work. There's no way that works. Light doesn't even go over there. Putting holes in your mirror is not going to do anything, and if you put the wrong holes in it, it's just going to make it worse. Which here, I guess, if you put the wrong holes in here too, could make it worse. But if you put them in the right places, you can get a better image. Okay? Oh, we're off the bonus. And that's the very weird thing about it. Now, you might be wondering, why don't we do this? Why don't we go around to all our mirrors and put holes in them? Well, it has to be specific for every case. If we move the light source, now the distances all changes, and the directions of all those arrows change when they get there, and the holes that we put there are now the holes that potentially would have been holes we would have wanted to keep, and the ones that we kept in the pieces of the mirror are now the ones that would be canceling out and would get a worse image. Plus, we see in a lot of different colors of light, which all have different wavelengths. So the rate and how fast their little arrows spin is different. So if we did blue light along a path, and then we did red light along that same path, when they get there, they'll be pointed in different directions. Like having different sized wheels where one little arrow is spinning a lot faster than the other one's spinning slowly. All right, they're going to be pointed in different directions. So you have to do this for the very specific setup that you have, for the very specific color of light that you have. As soon as you change anything, you got to go back and change the whole mirror and fix it. How many of you think this is, we're going to go through this real quick. Who thinks this was done and tried and it worked? Yeah. This has been done and tried and worked. And you put the holes in the right places, and the mirrors started giving better reflections for that specific setup. Okay? So that's pretty cool, isn't it? Now, this is where we get into what Feynman says. A lot of people look at this and they say, oh, it's all this quantum weirdness. I am not one of those people. I do not at all think that quantum necessarily tells us how the universe works. But it is a great tool. It is useful. These waves may not have anything to do with what actually happens when light travels or electrons orbit or whatever. It may not have anything to do with it, and it might just be a good tool for us to solve this, just mathematical to us. I don't think we should make philosophical decisions based on the outcomes of quantum mechanics. And, oh, quantum mechanics says this can happen and this can happen. It's just a tool, okay? And 100 years from now, we'll probably have a different tool that works a little better and tells us something different. So be very careful with that. And Richard Feynman was very big on that. He convinced me of this. If you ever want to listen to his lectures, he was such a popular lecturer, like not like me here. Like his rooms would fill up and people would be like cramming to get in there. Apparently he taught a general physics class, like what I teach here, and even other professors and graduate students started coming to his class. They weren't even enrolled in it, just to listen to him like speak, and he would like fill the room up talking about this stuff. So you can find those all online. They are very interesting. He's a pretty philosophical guy. Any questions on this? Yeah.
Do you know anything about knot theory?
About what?
Knot theory?
Like a K-N-O-T?
Yeah.
I don't know. I'm not great with names.
Okay.
What is it?
Well, it's like the study of knots, basically. Like loops. Like loops. If you were to tie it a string together, the loops that would, studying them on a graph. I just didn't know if there were any kind of relations between studying waves and knot theory that you knew of. Or
Not
like loops.
that I know of. I have never studied knot theory.
Yeah, it's a really specific field, so it was a long shot.
I got Trish with that. Professor Adams. Yeah.
Okay.
Sorry, I had to
you're
look
good.
into it, but that's a math thing, right?
Yeah, you're
I've
a
never
math
heard of
guy.
that in physics, Didn't really do that one in
Oh,
physics,
my
so.
other one was the harmonic series is correlated to what you were showing with the harmonic,
Yep.
right? Okay.
Absolutely. Absolutely.
That was all.
Anybody else? We have a little bit of bonus time. Do you want me to go to my couple of bonus slides?
Yes, absolutely.
Why not? Thank you, Mike.
You're welcome.
All right, bonus. I even put a question mark, like, would y'all want to hear this or not? Fancy question. So the Schrodinger equation. Y'all probably have heard of this, right? Erwin Schrodinger, the Schrodinger equation. We usually represent it with that Greek letter psi. Basically, what this thing is, and I put some of this in here for the math people, although I think there's only a few of you here now, a couple of you. This is an infinite dimensional vector. So we talked about those vectors, those ones I was showing you before, they were two-dimensional. They could point like left and right, or up and down. They were two-dimensional. You could have a three-dimensional one that points off in that direction. This thing is up to infinite dimensional. All right, kind of weird. I don't know how to draw that. I don't know how to picture it in my head. I know it works when you do the math. Okay, you can do it mathematically. Don't know how to represent it with a picture or anything like that, even though I give it a try here in a few minutes. Okay, this is a physical Hilbert space. So those of you in math will hear of Hilbert spaces. They're a little bit different. Normal Hilbert spaces, these infinite dimensional spaces, or up to infinite dimensional spaces, you can normalize them to unity. We physicists take it a step further. We have all that, but we can also normalize it to what is called the Dirac delta function. All right, that gives us what are called improper vectors that are in there. Mathematicians, when physicists first proposed this Dirac delta function, mathematicians were basically appalled. How can you do this? This is just made up. You have no reason for it, but it works. That was essentially the response of the physicists. It works, and it works very well. So I do think mathematicians use it now. But it's a very infinite, it's a very neat thing. It's essentially a function that is zero everywhere, except at one point where it's infinite, and if you find the area under it, it's always equal to 1. Very strange thing. Don't know how to represent that with a function or anything. We usually just write the delta, and it has certain properties that you can basically multiply it on something in light. You use it in integration, and it picks out a value at a specific point. It makes it very easy, and it works very well in quantum mechanics. Okay. In order to get this equation, we take this psi vector, you end up squaring it, you end up doing these things to it, and then you project it, okay? You project it, kind of like a shadow. If I hold my arm out like this and there was a shadow up here, you would see the length of my arm equal to the length of the shadow. If I moved my arm this way some, then my shadow would get shorter, even though the length of my arm is not, and if I go all the way over here, then it's like there's no shadow for my arm, right? That is like projecting it onto there. And then you could do the same thing. We could project a shadow this way and have a shadow over there on a perpendicular wall. And I'd start off with no shadow over there and a shadow the same length as my arm, and as I move this way, that shadow gets longer and this shadow gets shorter. And the idea is we can do that with this Schrodinger vector, this psi vector. And dependent upon what we project it into, so let's pretend that psi, that vector right there in the middle, this is our infinite dimensional vector, and we're going to project it onto some space, some other infinite dimensional basis. And then if you go and you look at the length of the shadow of that psi vector in every single possible place there, that length will tell you the likelihood of measuring that value. So if you look here, if we were trying to measure whatever L is, L2, ooh, wait, I put L2 twice.
And X3 twice.
And X3 twice, did I? Oh. So, this will be L3, that's X2 there. We would see that whatever this one is, we'll go with L3, that's the most likely thing you would measure. L1, least likely. That's the least likely value you would be to get if you measured whatever this system was for whatever L was. Okay? Be all kinds of different things. That'd be the least likely thing. And if you go through and do this for all the infinite dimensionals, you end up building a probability density along every single possible outcome. That's kind of where you get those probability kind of waves that occur. So we could take psi and we could also project it into a different basis. See how I changed it a little bit? And I changed it from x's to p's. And I didn't change it. I have D2 twice and P3 twice again as well here. So yeah. So we could say, like, so for example, this first one, this is position. So we try to measure where is our little electron. All right? And we make 1,000 identical setup electrons, and we go through and measure the position of each one of them. And if we then plotted out the locations of them, we get most of them are in L3, whatever that bottom one is, and the least of them ended up looking like that over, and we get that kind of a distribution spaced out. If we instead wanted to know what the momentum was of that particle, we could project it into the momentum basis. All right, you take that infinite measure, you project it into momentum, you look at the lengths of the shadows, and it tells you how likely you are to find those particular momentums. Okay? Obviously here, the bottom D2 is the most likely one you are to find, and you get these distributions. Okay? And I'm not sure what that little X1 is doing for the side either. I think I put these and thought, oh, I might show these. I'll go back and correct them later. I guess I didn't. So anyway, you get these different probability densities, and you get these psi squared values, and they tell you what the likelihood is of measuring a certain position or a certain momentum. All right, there they are side by side. It's the same psi. That psi vector contains all the information there is to know about that particle. That wave function, that infinite dimensional vector wave function thing. And you just project it into a basis and get the information out of it. And then when you want to go back and calculate how the waves interact, you go back to that psi thing, you add up all the vector things of that infinite dimensional psi, and then when you get your result for whatever interaction occurred, you project it back into whatever space you want to know information about and get that. Know after that interaction where it's most likely to be or what momentum it's most likely to have. And you can go through and do that. Okay? Now, A very interesting property, and oh my gosh, there is math. I have a minus sign there. I apologize. Is we have something called the uncertainty principle. Have we ever heard of that? The Heisenberg uncertainty principle. You can't know both the position and location, or the position and velocity of a particle at the same time. The more you know its position, the less you know its velocity, which is actually momentum. Because momentum, especially my physics students, MV has velocity in it. So it's really the more you know the position, the less you know the momentum, and the more you know the momentum, the less you can measure the position. It turns out, if you have two things, these are quantum operators that projected into these bases, if they do not commute, then it means that you can't measure both of those things at the same time. And by I mean commute, I mean if A times B minus B times A equals 0, then you can measure both of them. Okay? If they, when I wrote the wrong thing up there, I think then, if they commute, then you're out of luck. All right? And again, I should have gone back and looked at this. Okay? So position and momentum cannot be measured at the same time because they do not commute. This is the wrong line. Sorry again. All right? There are other ones, energy and time, that you cannot measure at the same. You can't. The more you measure energy, the less you can measure time, and the more you measure time, the less you can measure energy. And it's kind of weird to think of that, but we do have an actual physical interpretation of this. So take a look at this. We have two waves here. If you looked at that top wave and I asked you to tell me, where is that wave? You'd know where to point, wouldn't you? It has a very well-defined position. Correct? Mm-hmm. It's right there in the middle. You know? Oh yeah, it's right there. But now look at the second wave. Where is it? Where would you want to point exactly? It's a little fuzzy there, isn't it? I mean, do we point right in the middle or a little off to the side, or because it's not totally symmetric, so where do we point on this thing? Not entirely sure. Probably somewhere between the two ends, but it's not as exact anymore, right? It turns out the momentum of a wave, especially of a light wave, is based on its wavelength. So if you look at that top picture, can anybody tell me what its wavelength is there? How long is that wave? How wide is it? Kind of hard to measure, isn't it? Because it kind of just tapers off at the end. Where do you stop measuring the width of it? If you know anything about wavelengths, you need like a full crest and trough to measure. So we cannot measure that wavelength very well. We can measure that position very well. We cannot measure its wavelength, so we cannot measure its momentum very well. Very good position, very bad momentum. Next picture down. Not very good at getting a position for it, right? But boy, that looks like a pretty repeatable wavelength there that we could measure, doesn't it? So I think in that second one, we could figure out what the momentum of that wave was. So you see how the more well-defined we get of a position up there, the less we can get of a momentum. And the more well-defined of a momentum we get here, the more fuzzied out our position gets. And it turns out like that's what happens with position and momentum in quantum mechanics. I think that was like the best visualization I ever saw for that right there. Okay? And I think that's it. Any other questions on any of that bonus stuff? Sorry you stayed for it? Yeah? Yeah?
If we can't measure it at the same time, what's stopping us from just doing it twice?
You mean like measure the position?
Yeah.
Measuring it necessarily changes it affects the situation.
Okay.
So it changes it. So if I wanted to measure 1, I would measure it and I'd get a, like say I was measuring, I'd get a very clearly defined position, and there wouldn't be very, I'd try to measure momentum after that, except it would have it wouldn't be very good at it because it would be looking, did I lose the whole thing? What happened here? On my screen it's like back at the beginning. So that's where that direct delta comes in. It causes, why is it blank up there still? And we're back at the beginning. only 75 slides. Give me a second. Now let's go through the whole thing again, right? Oh.
Oh.
So, if you can remember those pictures, yeah, it'll collapse down. It's kind of like saying, let's say I had like a ping pong ball floating along and I wanted to measure that ping pong ball's position. So I use another ping pong ball to see it, right? So I have a particle going along and I shoot another particle at it and let it bounce off, which is like a photon a lot of times. It bounces off, light. It bounces off and comes back to my eye and I say, oh, that's where it was. Well, if I put in a very detailed, very high energy photon, I can, with a lot of detail to it, I can get a very accurate picture of what the position was. But by doing that, I hit it really hard, which changed its momentum. If I send in a nice, soft, gentle light to look at its momentum, right, I can't get a very good feel for its position. Kind of like, I want to measure that back wall. So I'm going to throw objects at it, like balls. Well, if I use ping pong balls, I can get a pretty fine map of the back wall. If I use basketballs, then I can't see it down below the size of a basketball, right? So there's that trade-off. And then so when I do make that measurement, it also changes this situation. It has an effect on it, changes the wave function, and now we're measuring a different system afterwards, depending on which way we changed it. We either destroyed more, we either changed the momentum more, or we changed the position more. Anybody else? Don't know what to ask? Or, I explained that so well, there's nothing to ask. That could be it, right? So really, nothing? We're good? So, sum up, just a mathematical tool that gives us some really weird results, and maybe one day we'll figure out a model that explains this and is much more intuitive, but right now, it's the best we have to give us good predictions we can do stuff with. So, yay, quantum. All right, guys, thanks for coming.
Is there a QR code when you scan it?
Oh, yeah, probably.
Do you want me to get their names?
Probably.
Oh.